That was not the proper audio subtitle or audio credit descriptor thing up at the top. This has just been my stream generic background music playlist. Collecting a bunch of stuff from various games. Currently, you're listening to Termite Capital from Bug Fables. If you ever actually want to check out the playlist I use for my stream backgrounds pretty regularly, I do actually have a playlist that's just like Stream BG, and it should be available on my channel. So like, if you just want to look at my playlist, it's out there. Anyways, hello everyone. How you doing tonight? I'm doing okay. I am sure as hell real worn out. But I am excited to watch some chemistry tonight at the very least. Yeah. I thought I had more things to say than that, but I didn't. Hey Gnarly, good evening. Yes, nice to see you here for the beginning of stream. It should be a good time. So yeah, I guess let's see. Tonight we have 2 videos on the docket, roughly each a half hour long. So I imagine I'm going to, well, half hour to 45 minutes. So I imagine I'll have some stuff to yap about to fill in the usual 2-hour stream slot here. In fact, I think we'll probably start off by yapping about some stuff. But yeah, the 2 videos we have tonight are Advanced Tinkering's Making a Blue Gas Again, which is chronicling his quest to make trifluoronitrosomethane, which I'll draw in a moment and I'll put up on screen and talk about for a little bit. But is interesting because, well, it is in fact a blue gas, naturally blue, without any electricity in it or anything. It's going to be pretty cool. And then there's also, from my favorite chemistry YouTuber out there, Extractions and Ire, / his main channel, Explosions and Fire, his video on gallium lanthanum sulfide glass, which, I don't know, is interesting to me. I, for some reason, have a fascination with non-typical glasses, because the glass in your windows or in your cups or pretty much any of your commercial stuff is going to be either completely silicate glass, so silicon and oxygen, or borosilicate, which is silicon, oxygen, and boron. You know, that combination is a little bit different, but that's basically all you're ever going to encounter out in the real world, or in the regular world. But in the lab and in a couple specialty applications, pretty much anything can be a glass. It just has to be the definition of a glass is an amorphous solid that is basically randomly structured. It's not orderly, but it is you know, not flowing anywhere. So like, it's a pretty loose definition. You could have a lot of things that are glasses. Metallic glasses are actually a really interesting material science pocket that I don't have, you know, we don't have a video to talk about tonight. Otherwise, I would love to yap about them for a while. But yeah, no, natural and blue. It's, I mean, it is in fact a gas that is naturally blue. And I know it's a little bit surprising because you often hear the moniker of like, well, there's nothing that's actually blue in nature, right? Like, you know, that in itself is a false generalization. I mean, people be like, well, blueberries aren't actually blue. It's like, that's true, but there are a very small handful of like there are blue orchids out there, which is actually an analogy for something extremely rare and not occurring, but there are a couple of them out there. There's also, of course, the blue-ringed octopus, and in our case, we have a gas that is itself naturally blue. Now, are you going to see it out in the real world? Absolutely not, but could you make it in the lab? Absolutely, yes. So, I guess that's where we'll start things off today. But first, I guess I have some yapping to do about the gas itself. So I'm going to maybe kind of, because I don't feel like redoing all the windows here, I'm going to maybe do something a little bit ratchet. Forgive me here, but just move that over, put that up. Wow, look at that. Now my drawing canvas is over here because I'm too lazy to redo everything. All right, well, I'm sure you don't want me standing around for 5 minutes while I just try to do stuff. So, let's introduce the topic for tonight. So, I guess, let's see. First video being, again, this is the I Was Wrong Blue VS video, which is going to talk about trifluoronitrosomethane. That is a molecule with a structure that looks like this. Carbon, fluorine, 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 bound to nitrogen, which is bound to oxygen. Drawing in my electrons as dots. If you remember your high school chemistry, these are lone pairs of electrons. And there you have it. So it's a pretty small structure, or pretty small molecule, and a relatively simple structure. I mean, it's only 6 atoms long. But it is an interesting gas because it is multicolored. Now you might ask, why is it multicolored? The answer is heavily quantum physics based, so bear with me as I do my best to explain this in like relatively grounded terms. I mean, I couldn't go into like, you know, I solved the Schrödinger wave function for like, no, I'm not a math genius ahead of his time. But I can talk about the orbital diagram, or the electron diagram. So, let's take a simpler molecule first to kind of discuss. I'm going to make another layer, and then make this a bit smaller. Get things started. Okay. So, that's our target molecule. But first, let's talk about kind of a simpler version, or a simpler related molecule of it. Nitrous oxide, which I believe y'all might know as a, laughing gas. Come on, please. There we go, paint. Alright, so nitrous oxide. Oh, that's way too big. Dot, 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 dot. Nitrous oxide has a structure that looks something like this. This structure comes from positions on the periodic table. A nitrogen atom would have 1, 2, 3, 4, 5 outer electrons. An oxygen atom would have 6, and each of these lines represents 2 electrons bonded together. To get this structure, you could solve the or to represent the structure in the best way possible, you can make a molecular orbital diagram, which is the combination of the orbitals on each atom overlapping to actually form what are chemical bonds. Orbitals are, for a ground level introduction, are the probability clouds where you might find a given electron that's on an atom. So the 1s orbit, or let's start with the 2s level, and there's so much here that like I couldn't cover in just a 1-2 hour video. But take it with me that the 2s orbital is a valid name, and for a given atom, it is a big sphere, basically. You have your atom in the center, and then you have all this 3-dimensional spherical area where you could have the electron found within that space. That's where like the 90% of the time it's going to end up being. And then similarly, you also have 2p orbitals, which instead of having this spherical shape, are dumbbell shaped, and they have a node in the middle, which mathematically / physically does the opposite, referred to as the opposite phase across the plane of the plane that bisects the dumbbell. And what you need to know about these is that they are directional. They kind of have this obvious point up and down to them. And likewise, they also come in all three orientations. So you have, you know, not only is this kind of your up and down like Y orbital, which I guess formerly we would call 2pY. You could then also have one that's in the Z direction, kind of in and out of the screen. Call that 2pZ. And you could also have one 2pX. Just be like this, horizontal to the screen, and that has a direction this way. This is important because these are the electron clouds that overlap between atoms to form bonds. So this double bond in between the nitrogen and nitrogen and oxygen molecule is one of these bonds is the s orbital of the nitrogen bonded with the hold on, let me draw that better. So you have your nitrogen here in the middle, or you have your nitrogen on the left, you have your oxygen on the right. The s orbitals combining look like this. Basically, they just form one big, large ovular shape around both of the atoms. Now, however, whenever orbitals bond, they also have an anti-bonding configuration. So that would happen if one of these, if the nitrogen circle had one phase, which will represent as kind of just, you know, a blank white color, and the oxygen had a the opposite phase, which will kind of just crosshatch in as like darkness. This is a configuration that does not cause a bond. It is the anti-bond, and if enough energy is put into the atom or the molecule, the bond would break because the electrons would go into this anti-bonding orbital. Now, with all that background out of the way, let me also, I guess, just sweep this up and put that in another layer. Great. So now with all that stuff about orbitals, you basically end up having the molecular orbital diagram look something like this. If we're going to represent the nitrogen atom over on the left, and we're going to represent the oxygen atom on the right, there are two s orbitals, and one of their 2p orbitals overlap, absorbing this all at once. Atomic theory is a passion of mine since you were a kid. Oh, hell yeah. Yeah, I mean, I've always loved chemistry since I was, like, really young. Like, legitimately, chemistry is something I've known I've always wanted to do since I was, like, in elementary school, or actually a little bit beforehand. And I just kind of so happened to know exactly what I like and what I want to do and what I'm good at very young. So it all kind of worked out. Everything's turning up Milhouse. So I'm glad to hear that like someone else has the fascination with chemistry as I do, because I just love this stuff. I think it's fascinating. Okay, so we have our 2p here and here. Of course, we have both 2p's, or I guess all three. So we, hold on. I'm trying to think about this. How does this exactly work? The s orbitals, it's been a long time since I've drawn a molecular orbital diagram, but okay, actually it would be then the s orbitals are bonded together, but then they also have the anti-bonding going on, so then the p orbitals, actually, the pz orbitals get to take a bond. They have a single bond, and then they have the double bonds. Okay. Alright. So the s orbitals try to bond together, form a sigma bond, which is that direct bond I was drawing earlier, but the anti-bonding orbital is also filled, so no bond actually forms between the s orbitals. But then you have the z orbitals, being the orbitals that kind of like face directly at each other in the NO. Those have electrons. Let's see, do I draw this simplified? Yeah, I'm kind of running out of space anyway, so I'll draw this a little simplified. 2px, Y. 2px, 2py. So the nitrogen on the left would then have 3 extra electrons. So we had 1, 2 down here. Periodic table would dictate that it has 5. 2, 3, 4, 5. And then the oxygen atom has exactly 1 more. So we have a total of 6 on the right side. Took you till you were older around high school. Felt really passionate explaining Crash. Thank you. It does help that I've also had to, TA classes, which requires a little bit of passion if you want even a slight hope of anyone paying attention. It doesn't always work either, but, you gotta give it your all, right? This. Okay. I don't know, I've always just found chemistry fascinating because it's just about, like, explaining, like, literally, how does everything around me just, like, work? Why do certain materials behave the way they do? Why do certain things look the way they do? Why do certain materials interact with each other the way they do? Why do we use, various types of metal for, like, cooking appliances? Why do we use plastic for this other thing? Why are bus handles made with metal? And it's like, oh, chemistry is good at answering all of that type of stuff. It's endlessly entertaining. Okay. Man, that took a little while. That took longer to draw than I thought it would, and a little bit messier. But, so now we have all these different orbitals combining to basically, form some bonds up here with the p electrons. So, with a total of 1, 2, 3, 4, 5, 6, 7, we would, 6, 7, we would fill this up, as much as we can with my, trying to do this with the limited drawing space I've left myself. So, 1, 2, 3... Or 1, 2, 3, 4, 5, 6, and then 7. So NO kind of gets this weird radical-like character, which kind of gets represented in this one lone electron up here. And basically, this results in a bond order, roughly a bond having, is this right? Hold on, I'm trying to think about this. God, this has been so long, I have not actually thought about this. Maybe I could just go check that real quick, do an online kind of Google, real thing. Of NO. Okay, yes, no, that's roughly correct. As you can see me checking my work in the background here. In fact, I probably should have just pulled this up. You end up getting a molecular orbital diagram that looks something like this. This is actually more accurate with all the calculations done correctly and formally. But this basically means the bond order is 2.5. So if we wanted to really draw this orbital the exact correct way, we would do something like, if we want to draw this bond the correct way, we just put like a dash thing kind of here. It's hard to draw on digitally for me. It's kind of like a half bond there. Okay, so all of this is to say that this, the kind of electron gap between pi and pi star over here, that would normally be something that could absorb UV light. And that's why you kind of end up getting nitrogen monoxide is like a clear, colorless gas. Of course, it oxidizes very quickly in air to nitrogen dioxide, which is brown, but that's a different story. When we take something, when we try to make this our trifluoronitrosomethane, that ends up becoming blue because the electron withdrawing properties of this big CF3 group ultimately lowers the energy of all the electrons on this side because the fluorines want the electrons so freaking badly. And as a result, that kind of narrows this distance between the pi and pi star orbitals. So whereas in nitrogen monoxide, this would absorb UV light, and since UV light isn't visible, we don't have an opposite like color on the color wheel for that. Our eyes interpret that as just blank clear. But if it absorbs instead, say orange light, once you attach the CF3 group to it, then it would start looking blue because our eyes say, oh, well, that lacks orange. That means it's blue. That's what the color blue is to us. So, yeah, that's a very long-winded explanation that literally took me nearly 20 minutes to basically say that's why this gas is blue. It is unusual, but also kind of elegant in its relative simplicity. I know I just rambled on for like 15 minutes to say a lot of words real fast, but in molecular orbital and atomic theory terms, this is simple. It just makes it so that way the pi and pi star orbitals here in the middle of NO are narrower, closer to each other, absorbs orange visible light, thus the molecule is blue. Ta-da! Cool. Let me catch up on the chat that I kind of looked past. You like to use chemistry to help understand stomach problems better? Yeah, no, that's actually pretty good too, because there's often times where it's just like, oh, something doesn't feel right. Did I eat something too acidic? Let me eat something basic, or like, it's fun that for some reason Pepto-Bismol, like the one thing Bismuth is biologically great for, apparently, is soaking up hydrochloric acid and other stomach upsetting problem children inside the gut. All right, so with all that, we can actually get to watching the video for the night. And let me just get the window back in its position. There we go. And we can get our layers ready. And we can actually get to watching. So, this is a companion piece video, actually. So, a couple months ago, I reacted to Advanced Tinkering's first video on this topic of making the blue gas, trifluoronitrosomethane. Because he actually wanted to do it initially because the image that was on Wikipedia was wrong. It was literally just a edited image to color shift the image for chlorine gas. So no one had ever made the video. And his previous video, he did a bunch of professional science in a professional laboratory to get a sample of this blue gas in a relatively dilute form. And it was kind of this, like, pale sky blue color. So it's like, okay, maybe the color's a little overrated. It's not this rich azure blue as we, as is reported. But we do have a new video here that seems to, counter that notion in the first place, where you can actually get a darker blue gas if you just get it concentrated enough. So I'm very interested to see how this shakes out for him. Also, I did just notice on my phone that I was like a minute behind on my own, I was a minute behind my own stream on my phone, so like, if y'all want to like take a minute to just like fast forward a little bit to make sure you're caught up with the stream and not waiting a minute for me to react to anything you type out, now would be a very good time to do so, as I shut off the music and we can get things going.
In my last video,
I that's a little bit quiet.
Called trifluoronitrosomethane to expose a fake photo on Wikipedia. If you saw that video, you already know the problem. The gas I made was blue, but it didn't really match what the literature said. According to the papers I found, it's supposed to be a deep blue gas. Mine was more of a light blue, almost cyan.
Well, there are papers out there that say I got an off-white solid when in reality it's like 25 shades of tan.
My sample back then was
so you can't
not
always trust
perfectly
literature.
pure. So there was always this annoying possibility in the back of my mind that the pure gas might actually be a deeper blue. I also mentioned that in the caption of the picture I uploaded to Wikipedia. But let's be honest, who actually reads image captions on Wikipedia?
I mean, you gotta click on them, so not really.
In the video I said that I believe the color would not change much if the gas were perfectly pure. But belief is not the same as proof. To make things worse, I got a comment from a viewer who said that his colleagues had worked with this gas over 30 years ago, and he remembered it as being more intensely blue. All of that slowly started to eat away at me.
The things I love about YouTube, its ability to still manage to connect people who are like, oh, wow, yeah, I remember I made this gas 35 years ago. Let me watch this guy who made this other video on the topic. What? He didn't quite make it right. Let me just break out the keyboard here.
What if the pure gas actually is deep blue and I'm the one spreading misinformation? Honestly, that's not something I could just ignore. So, I decided to do the only sensible thing. Make the gas again using a different synthetic route, clean it as much as I possibly can, and finally settle once and for all what the color of this gas really is.
Real dedicated chemists actually going back to clean things up.
I made trifluoronitrosomethane by shining UV light on a mixture of trifluoroiodomethane and nitric oxide. That works, but it has some drawbacks. Most importantly,
there were a lot
if
of
you
them.
want to produce larger amounts of gas, you need a very large flask.
And a lot
The method
of
I'm
mercury.
showing you today can, in principle, be scaled up much more easily so that you could make larger quantities of the gas. At least in theory. As you will see, in practice it turned out to be much less straightforward than expected.
Hey Chris,
the plan
welcome.
Was to first make
You're
this
pretty much right in
molecule.
time to
It's
start watching the video.
Trifluoroacetylnitride, and it can be directly converted into the blue gas. To make it, I first need this part of the molecule, which comes from a highly corrosive and toxic yellow gas called nitrosyl chloride.
Ugh.
Nitrosyl chloride is one of the compounds that forms when you mix nitric acid and hydrochloric acid to make so-called aqua regia.
Oh god, that is right. Oh, this is gonna be a very interesting synthesis then. Because, like, not only is just, like, looking at this trifluoroacetyl nitroso thing in the middle here, that's a really exotic kind of looking compound to me. Just like that ONO kind of configurations like that, not super stable on their own. To have that go further into like this halogenated electron withdrawing ester formation, very strange. And then so as he's explaining, this nitrosochloride is that's the active ingredient in aqua regia, the mixture of nitric acid and hydrochloric acid that is able to dissolve gold, one of the few acid combinations, but is kind of the most accessible considering it was known since antiquity, that can actually dissolve gold. And that is purely because this CLN bond is so tenuous. It is reactive even with amongst the most inert of metals there is. So to actually end up using that in a synthesis that's not just I'm gonna make, aurum chlorate or whatever it's trichloroorate. There it is. The like gold chlorine salt. Yeah. That's kind of unusual, and I'm here for it. This is unusual organic chemistry, and I'm loving it.
Which is strong enough to dissolve gold. However, since I needed pure nitrosyl chloride, I could not simply use aqua regia.
Really?
Instead, I had to use a different method to produce the pure gas.
You're gonna just mix the gases
For that,
themselves,
I
or
needed another toxic gas.
Oh hell yeah!
Nitrogen dioxide.
German chemicals.
When this gas reacts with potassium chloride, it forms nitrosyl chloride.
Did you know that German chemicals used to be the main thing, or Germany used to be the big chemical manufacturer before America did? So you go old enough in the chemical bottles you purchase, you might find just that most of them are written in primarily German, and then you get English a couple decades later.
But how do you make a gas react with a solid on a larger scale?
Yeah, it seems a little difficult. I
did.
mean, maybe pass it through a tube
I
full
took a
of
long
it?
glass tube. At the bottom, I connected the NO2 cylinder. Inside the tube, I would pack potassium chloride, and a bit of glass wool at the bottom keeps it in place.
That makes sense.
Before filling the tube, I had to moisten the potassium chloride with about 2.5% water.
Oh, a little bit of fouling.
So I put portions of potassium chloride into a mortar, added a small amount of water,
I
and
mean, I only
ground
say following
everything
because I'm sure it
thoroughly.
does not want water in
As
this
you can
final
see
product,
from
but
the UV reactor
you need to get
sitting
it
in
kind
the
of
fuel
solid.
hood, I was doing all of this in parallel with the synthesis route from the previous video. At that point, I was not sure whether that first route would actually be successful, so I wanted a backup running at the same time.
So the story he told at the beginning about like, oh, it was eating at me, it wasn't quite working, so I had to make a new video on the topic. It's like, no, you were doing both at the same time. Now that's actually good chemistry, and also is a very good representation of how papers are written, where you kind of do the science first and come up with the story afterwards to make it compelling to read.
After mixing the potassium chloride with water, it was no longer a dry powder, but a slightly sticky mass. I then packed it into the glass tube, making sure the filling was as even as possible so that the nitrogen dioxide would react uniformly along its length. The final
Nice.
setup looked like this. Nitrogen dioxide flows from the cylinder into the bottom of the tube, passes through the potassium chloride and reacts to form nitrosyl chloride and potassium nitrate. At the top of the tube, the nitrosyl chloride comes out and is let into a gas washing bottle filled with calcium chloride to dry it. The dry nitrosyl chloride then passes into a cold trap that is cooled to about -75°C, where it freezes out. Behind the cold trap, there is a second gas washing bottle filled with calcium chloride to prevent moisture from the air from entering the cold trap and reacting with the nitrosyl chloride.
Bravo. That's a pretty elegant
Once
setup
the
you got
entire
there, just to
apparatus
get
was
the
set up, I placed
gas
a
to pass
dewar
through
filled
properly.
with the
I haven't had to work with much gas phase chemistry in my time at grad school, undergrad, anything like that. But it is honestly pretty tricky stuff to do. I only used to ever have to just work in air-free environments, which is like there's a standardized setup called a Schlenk line to work with that, and that's a little complicated to operate. But this is a million times more difficult. I mean, literally, he's setting up tubes upon tubes upon tubes of stuff to try to isolate his product, which is completely unstable and needs liquid nitrogen temperatures to exist for even a temporary period of time. Yeah, kind of difficult.
cooling mixture under the cold trap and slowly opened the gas cylinder. You can see the orange-brown NO2 flowing into the tube. As soon as it hits the potassium chloride, the color fades and turns yellowish. You can even feel the outside of the tube getting warm from the reaction. Slowly, the whole tube
It's not every day you
fills
get
with
to see
yellow
something
nitrosyl
react with a
chloride.
salt like that. That isn't just
After a
dissolving it.
while, the gas reaches the first gas washing bottle. Here you can clearly see the color difference between nitrogen dioxide and nitrosyl chloride. The NO2 going in
That
has
source
a more
of
brownish red
Aquarege's
color,
kind of
and the
disgusting color
nitrosyl
comes from.
chloride coming out is clearly yellow. After drying, the nitrosyl chloride condenses in the cold trap as an orange-red liquid. The color changes are actually very useful. You can see the reaction front crawling up the tube and it tells you exactly where the potassium chloride has already been consumed. It is important
And therefore
to
when
stop
to turn
the
off the
reaction
bottle.
before the NO2 reaches the top of the tube in order to avoid contamination of the nitrosyl chloride with NO2. This reaction takes quite a while.
Wow, that's
So,
dark
in
red.
the meantime, I started making the second compound I needed, silver trifluoroacetate. And I made it starting from
Commercially
this silver
available,
bar.
but I guess
Even
less
though
expensive
it
to make
looks
on your
very
own.
nice, I had to turn it into a brown powder, silver oxide. To do that, I first had to prepare silver nitrate. So, I placed the bar in a beaker, added a bit of distilled water, and then nitric acid. At first, not much happened. You could only see a few bubbles forming on the metal surface and the acid turning slightly yellow. To speed up the reaction, I decided to heat the beaker on a hot plate. After a short time, the reaction became much more vigorous and brownish red fumes
Classic high
started
school
to rise
demonstration.
from the
I mean, if your high school is enough
Those
money to
are
purchase silver.
nitrogen oxides, mostly
More likely to
nitrogen
do copper.
dioxide. Yes, the same gas I was using to make nitrosyl chloride. Once the silver
Anything
bar
interesting
had
happening lately?
completely dissolved, I left the solution
Not
to
really,
cool
honestly.
overnight.
But this isn't
By
really
the
the place
next
to yap. I have
morning,
maybe a couple
beautiful
stories, but
silver nitrate
it's
crystals
not
had
the best
formed
place to
at the
yap
bottom
over
of
the
beaker.
video.
From there, I could finally make
The
silver oxide.
downside of React streams, it's literally just I have to focus on the video and talk about it rather than, you know, yap
I
about
filled
my
a
interesting
large
things lately.
bottle with distilled water
I can
and
kind of use the
added
break, to be
sodium
honest.
hydroxide. After it had fully dissolved, I slowly poured the silver nitrate solution into the bottle while stirring. Immediately, a brown solid started to form. That is silver oxide. Once all the silver nitrate
delicious.
solution had been added, I stopped stirring
The
and
rust
let
of
the
silver.
solid settle to the bottom. Then I poured the liquid through a filter, making sure not to pour too much of the solid into the filter at once so it would not clog immediately and slow down the filtration too much.
Oh, and he's doing
Once
it by
the liquid
gravity
was
as well,
removed,
instead
I
of using
rinsed the
vacuum
solid
filtration.
thoroughly with distilled water
Surprise,
to
would have
wash
been
out
quicker. I mean, he
any
literally
leftover
has a
sodium
proper fume hood.
hydroxide.
He could
To
easily
dry
do
the
a vacuum
silver oxide,
filtration, do
I
it
put
way
the wet
faster.
product into a vacuum oven. As the name suggests, it is an oven that you can evacuate so that water is removed quickly. After about a day, I had nicely dried silver oxide. From this, I could finally make what I actually needed: silver trifluoroacetate. In a round bottom flask, I added distilled water and slowly dripped in trifluoroacetic anhydride. It reacts with the water to give trifluoroacetic acid.
Man, that is alright. That is a very angry chemical. I will draw that as the I guess as he monologues on.
I could have used the acid directly, but I only had the anhydride on hand. To this acid, I added the freshly made silver oxide. In a neutralization reaction, silver trifluoroacetate and water are formed. After I had added all the silver oxide, I had to remove the excess acid and water. So I connected the flask to the vacuum line through a cold trap. The water in the flask evaporates and freezes out in the trap. If you look in the background, you can still see the nitrosyl chloride synthesis running. Once the silver trifluoroacetate was completely dry, I transferred it from the flask into a jar for storage until I needed it.
Yeah, but then basically that reaction works by the water kind of breaks up the trifluoroacetic anhydride here, makes two trifluoroacetate anions, and then those will bind with the silver ions as well, and you'll get some water byproduct that needs to be taken away. Looks like coffee. Kinda. Probably tastes way more bitter than it though. Hey, Amzro, welcome. We're in the middle of the video that makes a blue gas trifluoronitrosomethane. This thing up in the upper left corner there. It's naturally blue, and he's doing all the preparatory steps to get there.
To slightly gray. In my case, it was brown, because I also had to use some older, impure silver oxide, since the amount I made myself wasn't enough.
So you ended up using someone else's
problem,
crap.
though, because the next
crap
reaction
anyways.
would clean it up
Well,
anyway.
it happens.
Now that the silver trifluoroacetate was ready, it was time to check on the nitrosyl chloride. And it looked like I had collected enough for
frozen
the
a
next
bit
step.
too.
To temporarily store the nitrosyl chloride, I decided to condense it into a smaller vessel. That was absolutely the main reason.
Also, it's funny how he's
and
finally
not
wearing
at
gloves
all
in
the
this
fact
video.
that
I can't
had
remember if I
forgotten
think
to
he wasn't
weigh
wearing
the
them
empty
last
cold
time.
trap, so I had no idea how much nitrosyl chloride
It's like,
exactly
oh man,
I had collected.
the really corrosive
To
stuff. Better put on
transfer
some
it,
gloves.
I first froze the
I'd
nitrosyl
do a
chloride
little
in liquid nitrogen.
more protective than that.
Then I connected the cold trap to a smaller Schlenk flask whose weight I had measured beforehand. Because the nitrosyl chloride was cooled in liquid nitrogen,
Yeah, I agree. It's pretty
I could
bad.
evacuate the entire setup, including the cold trap, without losing any product. If I didn't evacuate the apparatus, I would both condense air and moisture into the smaller flask, and the
That's so
transfer
good.
would take much longer. This is the standard approach whenever you transfer substances under vacuum from one vessel to another by condensation. So I will not mention it separately every time from now on. After evacuating, I removed the door under the cold trap and instead cooled the Schlenk flask with liquid nitrogen. It is interesting to see that the nitrosyl chloride, which is a deep red liquid, is yellow as a solid when frozen. Once all the nitrosyl chloride had been
maybe it
transferred
expands
into the smaller
or
flask,
bond.
it was time for the next step.
I would imagine the color change from red to yellow from liquid to solid is probably due to like how when water freezes, it goes from being disorganized to organized in like hexagonal patterns. So I imagine that this nitrosyl chloride freezes in a manner that orders the molecule a bit more, so that way there's more bonding in between each individual unit, and thus you get again this shift in orbitals, like how I was drawing it earlier for the target molecule we're making, and you get something that's like, well, now instead of absorbing dark green light, it absorbs something closer to like maybe a light green light, or getting closer to like cyan kind of territory. Just due to how the bonding changes from the liquid to solid phase.
Reacting it with the silver trifluoroacetate. This forms trifluoroacetyl nitride and silver chloride. The nitride is the direct precursor to trifluoronitrosomethane, the blue gas. So I first ground the silver trifluoroacetate into a fine powder in a mortar. This is important because it reacts as a solid with liquid nitrosyl chloride, so a high surface area is crucial.
It will make it go a lot faster.
I placed the fine powder into a round bottom flask. To transfer the nitrosyl chloride, I connected the two flasks with a hose. Then I cooled the silver trifluoroacetate flask with liquid nitrogen so that the nitrosyl chloride would condense into it. You can
right.
See
you don't want warm solid because that'll make it boil off.
Tasty.
It won't actually react very well. I'm sorry, did he just say that looks tasty?
It almost looks tasty.
I don't know. I think we have very different perceptions on what colors look tasty, because to me that looks like it's angry, kind of like a hot sauce that's not designed to be fun to eat but designed to kill you.
Chloride, I prepared a cooling bath
or
by
just
cooling
pure poison
isopropanol to about -20°C using liquid nitrogen. When all the nitrosyl chloride had condensed into the reaction flask, I swapped
now the light blue gas, that's gonna look tasty.
-20°C
and look like a delicious Skittle.
Isopropanol bath. That way, the nitrosyl chloride melts and can react with the silver trifluoroacetate, but the temperature is still low enough to stop it from evaporating and overpressurizing the flask. I left this reaction mixture at -20°C for about 2.5 hours, occasionally swirling the flask vigorously to ensure good mixing. After that, I needed to get rid of the excess nitrosyl chloride, because it would be a problem in the next step. For this, I connected a second hose through which I could pass argon through the flask.
You wouldn't want to just
then I allowed the flask through
you
which
could see the
through the flask.
I think you can just barely see the brown plume kind of coming out above the argon flask here. Or above the kind of argon pushed or argon assisted evacuation of the flask here. It's kind of nasty. But yeah, you wouldn't just want to evacuate this by opening up to the air, because the product that he's making, let's see here. Let's redraw that again real quick. That product he's making is CF3. NO. This part of the molecule be very air reactive. So fun fact, I guess, is that when you have nitrogen monoxide in air, that will react with oxygen, and ignore the half reaction stoichiometry. We're just kind of doing this quick and dirty, to form NO2 gas. So basically, this section is very prone to reaction with oxygen. So if you just open this straight to the air instead of kind of trying to pass the excess NOCl gas to the air, then if you just tried to vent this directly to the air, you'd also end up reacting your entire product with oxygen here, which you only really want to react this with the oxygen out, which is the brown off gas that you're kind of seeing in the video there. So yeah, that's why it's doing that.
Flask. Then I allowed the flask to warm up to room temperature so that the nitrosyl chloride became gaseous and was carried out by
you
the
see the brown a lot better there.
In this way, the nitrosyl chloride was safely disposed of into the into the chemist's bin.
Safely.
Once no orange, red fumes were visible
I'm sure your
anymore,
HVAC guys really appreciate
the
that.
nitrosyl chloride was gone. When I looked into the flask, there was no liquid visible, only a yellowish solid. So I started to worry that the reaction might not have worked. There was only one way to find out. I connected a new Schlenk flask to the reaction flask via a hose, cooled it with liquid nitrogen, and gently warmed the reaction flask in a warm water bath.
Yeah, now should be the easy
part.
part.
After a little while, I saw droplets of a yellow liquid forming in the cold Schlenk flask. So, it looked like the reaction had worked. It turned out though that connecting the flasks with a hose was a bad idea.
Oh.
Even at 125 millibar, trifluoroacetylnitride still has a boiling point of about 47 degrees Celsius. So it really prefers to condense in the hose and run back into the reaction flask. If I had connected the two flasks with a short glass tube instead, the distance would have been much shorter and I could have simply heated the tube with a heating band to prevent the product from condensing there. With the help of two heat guns aimed at the hose, I eventually managed to transfer most of the product into the second flask. It just took a lot longer than
I think he's just doing this to kind of separate it from whatever other
a usable amount of
crap side products might have been in the other thing.
I was now only one step away from the blue gas. That last step, however, turned out to be the most time-consuming.
Really?
If you heat trifluoroacetylnitride to around 190 degrees Celsius, it decomposes to form trifluoronitrosomethane and CO2.
Yeah, I thought that would be easy, all things considered.
I first have to evaporate the acetylnitride and then pass the gas through a so-called pyrolysis tube. In this tube, the gas gets hot enough to decompose, and the products can then be condensed in a series of cold traps. Unfortunately, the lab did not have a tube with the exact dimensions described in the literature. All their tubes were too long and too wide. Luckily, the lab has a large collection of different glass tubes, which meant I could make my own pyrolysis tube. I took a short glass.
All right, good. He's gonna do some glass blowing. But yeah, I guess the chemistry there is just literally heating this up should cause this kind of middle CO2 kind of structure here to just leave, because carbon dioxide is a very stable molecule. And if it's a very stable molecule, that means it will release a lot of energy to kind of separate itself off from other constituent pieces, which is energetically favorable. The reaction wants to occur, and therefore it should be pretty easy to just off gas and get out of there with some heat. I'm surprised this takes such a high heat. I didn't think this molecule was that stable, but I guess that just is how chemistry goes sometimes.
Glass tube with NS14 joints on both ends, scored it in the middle with a glass cutter, and then used a hot drop of glass to snap it in half. Then I did the same with a longer piece of tube to get a segment of the right length. The plan was to fuse the joints onto the ends of this segment. This lab does a lot of work with quartz, so they have a hydrogen-oxygen torch. It gets much hotter than the propane-oxygen torches I'm familiar with. That's great.
Also doing this without any
a
heat
while to
protection
get
gloves.
used to it. The
Just
second
if you
fused
get
joint
burned, fuck
looked
it.
better than the first one, but it was still far from beautiful. It did not have to be pretty though, it just had to work. You don't have to be proud of everything you make. With
Lies.
pyrolysis
Everything
tube
has to be
ready,
perfect.
it was finally time to set up the apparatus for generating the blue gas. I connected the tube to a 2-neck flask using a 90-degree adapter. After the tube, I connected 3 cold traps in series. I wrapped the tube with a heating band and placed a temperature sensor between the band and the glass so I could monitor the temperature.
Okay.
Then
So,
I wrapped the whole thing in aluminum.
So that heating band that he put on there is basically just like a resistive series of wires inside of something like insulative, so that way it like traps the heat that is produced by electricity. But like to me, it always looks just very funny. Like I don't know why. Whenever I look at that heating band kind of apparatus, I mean, it doesn't help that usually they're all fucking blown out and old and from the 70s, like this giant hole indicates in his heating band. But like to me, it just looks like somebody is like wrapping their used rags and towels and like just the nastiest, grodiest thing they could find in the lab, and it just gives everything this like abandoned pirate ship look to me. I really wish people took better care of these damn things.
Foil for better insulation. Under each cold trap, I placed a dewar. The first dewar immediately after the pyrolysis tube would be filled with a dry ice isopropanol bath to catch easy to condense impurities. The second and third traps would be cooled with liquid nitrogen to condense the blue gas. At least that was the plan. You will see soon why this did not work quite as expected.
Well, I'm guessing
Under
that
the
any
2-neck
impurities are
flask,
going to
I
get stuck in
placed
the
a
liquid
hot
nitrogen
plate
gas
to
too,
be able to heat the flask
unless it's the
later.
reverse order.
Then it was time to
Probably it's the
transfer
reverse
the
order.
trifluoroacetyl nitride.
So I said first, second,
People
and third.
often ask how to transfer air and moisture-sensitive compounds from one flask to another. Besides the condensation method you have already seen, using a syringe is another good option. So I connected the flask with the nitride to the Schlenk line and flushed it with argon.
Okay.
Then I flushed a syringe with argon to remove any air
That's
and drew up
a
the trifluoroacetyl.
bit of a delicate balance he's pulling right there. There's just a slight flow of argon gas coming out from the black tube and going towards the syringe, and that blanket needs to be maintained to kind of maintain a barrier between the oxygen-rich atmosphere that we all live and operate in and the oxygen-free atmosphere inside the tube. If too much oxygen gets in there, the entire reagent, this trifluoroacetyl nitroso thing, is ruined.
Acetyl nitride. Before injecting it into the flask, I evacuated and flushed the entire apparatus and the flask.
This one's
with
doing the
argon.
exact same thing. Argon blowing
One
out the
mistake
open
that
neck.
people often make when emptying syringes, and that really makes my heart race, is not holding onto the needle while pushing the plunger.
Yeah, that
The
could
needle
pop
can
right
come
off.
and the contents of the syringe will spray everywhere. Depending on what you're transferring, that ranges from mildly annoying to very, very dangerous.
To deadly.
Once the nitride was in the
Literally,
2-neck
people
flask,
have
I
died
attached a
from
gas inlet tube to the
their
second neck
syringes
of the flask.
just flying right off when they're handling a reagent that literally ignites and explodes in air. So that is a good safety tip from the guy who was just blowing glass, who was just glass blowing without heat-resistant gloves a moment ago.
Later, I would bubble a gentle nitrogen stream through the liquid to carry the vapor towards the hot pyrolysis tube. I filled the first cold trap with a dry ice isopropanol mixture, the other two with liquid nitrogen, and turned on the heating band. To make sure enough nitride was carried along by the nitrogen stream, I heated the flask to about 75 degrees Celsius. After a short time, I noticed a serious problem. You cannot see it very clearly on camera, but in the liquid nitrogen cold traps, something was condensing that behaved like liquid nitrogen. In other words, the nitrogen from my carrier gas seemed to be condensing in the cold trap.
Yeah,
That
I
is
mean,
really not what you want.
yeah, no, unfortunately, that does make sense. If you do use liquid nitrogen as a trap, there is a chance that the nitrogen in the gas will just take some of the cold that's in the liquid and become a solid. Well, it won't become a solid, it would become a liquid itself. I guess there must be something else kind of freezing in there. Maybe the nitrogen's impure or something. Let's
Cold
see.
trap would quickly fill up with liquid nitrogen, so there would be no room for the blue gas. And on top of that, condensed nitrogen in a glass system can be quite dangerous. If it warms up even a little and starts to expand, your glassware can explode. This
God, liquid
completely
nitrogen's so pretty.
confused me. Under normal conditions, nitrogen should not condense in liquid nitrogen. Just like you would not expect water to condense on a surface that is at 100 degrees Celsius. While editing this video, another explanation came to mind. It might not have been nitrogen, but argon. I had flushed the apparatus with argon earlier, and argon does condense in liquid nitrogen. However, at those temperatures, argon would be a solid, not a liquid. So that explanation isn't very satisfying either. If you have any ideas, let me know in the comments. Regardless of what the problem actually was, I needed to find a solution. My solution was to use a different cooling mixture.
I mean, it was probably, if anything, I mean, it looked pretty solid in the tube to me. If anything, it was just kind of like a slurry, maybe. I mean, that argon, that frozen argon he just pulled out of the liquid nitrogen vat that he just kind of artificially did there, that looked pretty goopy to me. So I could see that just being condensed argon of some form in his cold trap.
Mixed with petroleum ether.
Oh,
this
that's what
gets me to around
ether.
minus
Never mind.
150 degrees Celsius. That is still cold enough to condense
He's
the blue gas, but
10 steps
not
ahead of me.
cold enough to condense nitrogen or argon. All of this took quite a while. Once the setup was finally stable, I could only run the pyrolysis for about 2 hours before I had to stop for the day. By that point, you could already see some greenish blue and orange condensate in the cold trap.
Yeah, pretty colors.
I condensed whatever product I had collected into a Schlenk tube. Interestingly, the tube ended up containing far more of a green compound than of the blue trifluoronitrosomethane.
That seems a bit concerning.
Since the gas would generate too much pressure if warmed up to room temperature, I stored the Schlenk tube overnight in a freezer at minus 90 degrees Celsius. When I took it out the next day, you could see a good example of why you shouldn't store flasks with PTFE stopcocks in a freezer. Because PTFE and glass expand and contract differently, these joints are never 100% tight.
Such as cold item with bare hands.
Into the space behind the stopcock. I expected that, so I added a glass stopper with a strong clamp on top, and fortunately none of the gas escaped. I then ran the pyrolysis for the entire next day.
Puts thing in liquid nitrogen, splashes up, again not wearing cryo gloves.
Working on the first synthesis route at the same time. At the end of the day, I finally had a noticeable amount of a light blue liquid or solid in the cold trap, along with lots of yellow-green impurities. It looks like more than it actually is, but we will get to that later. I also condensed that.
Yeah, impurities can, honestly, impurities really can actually build up to form a deceptive volume. I do remember in my grad school, I was making one of my compounds I was making was very blue and also had a lot of green and orange kind of like impurity streaks in there. And I could wash that thing endlessly. It's like for an entire day with solvents that it wouldn't dissolve in what the impurities were. And I could just always get more impurity out. I feel like at a certain point it was just decomposing spontaneously. And I was just washing more and more and more of it away. It's kind of a pain in the ass sometimes.
To the same Schlenk tube, and to roughly separate the impurities, I made sure to close the tube as soon as there was no blue material left in the trap. At that point, it was clear that my first synthesis route was going to work and I needed to focus on finishing it. So I decided to not further purify the gas at this stage, but to simply seal it in an ampule. I connected that ampule to the Schlenk tube and condensed the gas into it.
Ampule making is always such a...
the bottom of the ampule in liquid nitrogen.
I don't know why. It always looks cool to me. It's because it's literally just doing an active glass pull like that to be like,
glass softened
close
enough,
gas,
I removed
or
the duo
close
and pulled
glass
off the top of the
container.
it stays cold long enough that the gas does not have time to evaporate. The result was, as in my previous video, a gas that looks more cyan than deep blue. At that point, I was actually fairly happy. The gas from the other route was beautiful. But as I said in the beginning of the video, over time I became more and more skeptical. And the question became, do I really want to spend a lot of money on a rental car again and drive over 2 hours every day just to resolve this nagging doubt?
Well, when a doubt nags at you like that.
I'm on my way back to Marburg. I just have to know. I can't sleep well without knowing what color this gas really has. So, let's go.
This is what science does to a motherfucker.
Started, I want to tell you about the sponsor of today's
video.
Okay, Radiacode.
There's a sponsor to be like, yes, I need to get a fucking radiation detector for my home. What? No.
They are not only much more sensitive,
I imagine this has to be selling to specifically like chemists or hobby chemists or something. This is beyond what I would need.
You can combine that with GPS
almost anybody
data
would need.
to had some trifluoroacetyl nitrates. If you're interested in getting one, you will find a link in the video description. And now, back to the video. From the previous run, I still had some trifluoroacetyl nitrite left. Not much, but maybe enough to make a very clean sample of the gas. For some reason, the nitrite had turned slightly green. I do not know exactly why.
It's what happened to the other tube that you ampuled up.
Things just changed color for no apparent reason.
Just not gonna purify that again, or are you just redoing the entire reaction?
Setup as before, with one
I guess just gonna redo the entire reaction. Screw it.
This time I only used 2 cold traps because in the previous run no trifluoronitrosomethane had made it into the 3rd trap. One general problem with the pyrolysis was that a lot of trifluoroacetyl nitrite did not react in the hot tube at all, but simply condensed unchanged in the first trap. So several times I had to stop, warm up the trap and transfer the nitrite back into the 2-neck flask. According to the original paper, they managed to pyrolyze almost 25 grams of trifluoroacetyl nitrite in 3.5 hours.
Well, they probably had an industrial oven baking for like 3 hours.
My setup was basically the same as what they described. The only difference is that in their setup, they had a 1mm capillary between the flask and the pyrolysis tube. There are certainly several improvements.
Well, the 1mm capillary between a flask and the pyrolysis tube would allow for a very narrow gap, a very small surface area to volume ratio. So like you would actually have a lot more surface, which is more conductive, interacting with the flowing gas to actually get the heat breakdown necessary to forward the reaction. But, you know, in this case, doing a wide ground glass joint like that, while not a terrible idea, it is not as restrictive, therefore you're not going to get as much reaction going on.
That could be made to the setup, but at that point, I simply did not have the time to redesign the apparatus and optimize the synthesis. So I just kept going.
Sometimes working harder is better than working smarter. I agree.
At the end of each day, I transferred the nitrite back into the main flask and condensed the collected blue gas into a Schlenk tube. What I ended up with was a frozen solid that was again a light blue color, very similar to what I had seen in the first route, starting from trifluoroiodomethane.
But still with that kind of weird green band.
There were also a few impurities visible, most likely CO2, unreacted trifluoroacetyl nitrite, and nitrogen oxides. The good news is that all of these impurities are quite easy to remove. Either they have different boiling points, or they are water soluble and can be neutralized with a sodium hydroxide solution.
Oh, so now we actually can introduce water to this.
I filled a 2-liter flask with distilled water and added sodium hydroxide to make a 4% solution. Then I let the gas from the Schlenk tube flow into the flask, and as soon as there was no blue liquid left in the tube, I closed it.
Sometimes it's
yellowish
fun when you have
impurity
a
remained behind.
reagent that's reacted
I
with
then
oxygen,
shook
but
the
not with
flask
water.
to neutralize the CO2
Usually
and
it's both,
dissolve other
but
impurities
sometimes it's
in
not.
the solution.
This is one of those
To
cases
get
where
the
it's
blue
actually
gas
useful.
back out again into a clean Schlenk tube, I first froze the water in the flask with liquid nitrogen. This is a simple way to reduce how much water can evaporate along with the gas.
Freeze.
The wall
Always fun
of
to
the
watch.
flask became cold enough that the blue gas also condensed.
Oh,
And
well,
even at this stage, after just
that is
one
very blue.
purification step,
His color.
you can see that the solid or liquid has a very nice deep blue
This
color.
camera can't even really handle how blue
After
it is.
condensing the gas back into the Schlenk tube, you can also see that it looks much cleaner than before. The intensity of the blue color depends a lot on the lighting and on the thickness of the layer. Interestingly, the first Schlenk tube that held the impure sample had turned cloudy. It looks like
It
the
got
glass
etched.
has been attacked by hydrofluoric acid, which suggests that at least some carbon-fluorine bonds are being broken somewhere in the process. I found that quite interesting.
Probably, I would imagine, just due to all of the nitrogen, oxygen, or was it nitrogen monoxide kind of moieties being liberated during the cold and heat, and then also the light coming in. The light's probably breaking some of this like oxygen nitrogen bond and freeing some of these nitrogen monoxide species. That forms a free radical. Nitrogen monoxide having a lone electron over here on the nitrogen. And while carbon fluorine bonds are normally fortresses that are almost unassailable by chemical and physical means, the great thing about having free radicals is that these things are absolutely so desperate to find another electron to pair up with that, yeah, I could see it actually attacking a carbon fluorine bond and liberating a fluorine, and that goes on to find a hydrogen somewhere, and that starts etching away at the glass, which is hydrofluoric acid's real nasty stuff. It tears away at your nerves and your bones and gives you calcium poisoning, and gives you calcium deficiency from making all the calcium in your blood deposit out. So it's highly toxic, highly etching. Yeah, I could see that coming from the light just slowly interacting, forcing some nitrogen monoxide off, and then that forces some fluorine off of the material as well.
The gas, I again condensed it into a smaller 250 milliliter flask filled with a sodium hydroxide solution and stirred it vigorously with a magnetic stir bar for 30 minutes. Because the pyrolysis had taken such a long time, I split the purification into two portions. What you are seeing here is roughly half of the total gas I had collected. So yes, the yield was abysmal. At this point,
Well, at least
I
it's pure.
still did not know if I
Pure.
even had enough gas to fill a 100 milliliter flask to 1 atmosphere. If I did not, all my work would have been for nothing, because then it would still not be clear whether the gas might look more deeply blue at normal pressure. But there was no way around it. I had to keep going. After half an hour of stirring, I condensed the gas into an even smaller, clean Schlenk tube. Even though the apparent color still depends on the layer thickness, you can already see that the condensed liquid is much cleaner and has a deep blue color. Then it was finally time
look
to
at that.
test how
No little
pure
bits of
the
green
gas
in it
is.
either.
To check the purity, I recorded an IR spectrum. The sample from my last video still had a noticeable impurity in it, so I was really hoping this new one would finally be clean. To record an IR spectrum of a gas, I need a special cell like this.
Yeah, I've never actually
It
done
can
IR
be filled with
spectroscopy on a gas
and has
before.
diamond
That's
windows,
different.
so the IR light can pass through the sample. I connected this cell to the Schlenk tube, evacuated it, and filled it with the blue gas.
That's so cool looking.
Then I put the cell into an IR spectrometer and
But I guess just for background, what he's doing, he is taking an IR spectrum of an infrared light spectrum of the material. This basically involves with some complicated optical systems, to make this all work and reflect properly. Shooting your sample with infrared light and then detecting the light that is able to make it through the sample and reflect back at a detector. So it's basically measuring, um, and then that detector will tell you how much light was absorbed versus the amount of light that was initially shot at the sample. So you essentially get a diagram of peaks and valleys plotted against wavelength, and it'll tell you which wavelengths the molecule is absorbing especially strongly in. That correlates to the structure of the molecule and the various groups of atoms that are within. And so he should be able to basically get a fingerprint of the molecule, which thankfully, because other people have made this pure in the past, he can basically reference it against to say, did I get a very pure substance? Is it pure like the literature says it is? And based on the title of the video, I'm guessing he did.
Started the measurement. As you can see, the
Ooh, yeah, look
impurity
at
that showed
that.
up
That's
in
clean.
my previous sample is completely gone. You can still spot a tiny trace of CO2 though.
That's pretty
That
hard to get
could
rid of.
either be leftover CO2 in the gas itself or simply a change in the CO2 concentration inside the spectrometer compared to the background measurement.
Yeah, I get, because that's also a thing. You have to do a background measurement, and because the air is full of CO2, that's a really hard one to get rid of. And I mean, also like just as a reaction alone, yes, CO2 is water soluble. It's not that water soluble, obviously, right? Like carbonated drinks exist, but the carbon dioxide does like to kind of leak back out. Now, granted, I'll give you that is something about like carbonating it under pressure, and then the carbon dioxide will slowly leak out over time. But still, carbon dioxide is only so soluble in water. On the scale of oceans, yeah, it's soluble. On the scale of a flask, eh, you could maybe get a little bit out. You'd have to do a lot of water washings, probably.
Just breathing next to the instrument sample chamber is enough to give you a CO2 signal. As for the other small impurity, I can't say for sure what it is. It might be N2O, also known as laughing gas, but that's pure speculation
Oh, damn,
on my
that's
part.
laughing gas? Oh, I said
To
that
make
wrong earlier.
sure there was no CO2 left, I washed the gas again with a sodium hydroxide solution. These impurities mean the sample still isn't absolutely pure, but IR spectroscopy is very sensitive even to traces of contaminants. And I don't see any fraction with a boiling point different from the blue gas itself. So I'm confident
forming
that
a zeotrope.
whatever impurities remain are minimal.
Wants to
Since I
flow over
only
with
had
the
a very
compound.
small amount of the blue gas left and not enough time to make more, I decided to not chase down those last traces of other compounds. But I genuinely encourage anyone to repeat the synthesis and either confirm
Oh yeah,
or
anyone.
disprove the results.
Someone
I'm
can
about to
very
show you.
easily replicate this in their garage,
After
I'm
washing
sure.
the gas again, I condensed it back into the Schlenk tube, and it was finally time to seal the gas in an ampule to see what the color really looks like. But there was one small problem.
Oh,
That
no.
tiny puddle
Another
of
problem.
liquid at the bottom of the Schlenk tube was all I had left. I really did not want to risk putting it into a 100 milliliter flask and then discovering that it wasn't enough to reach 1 bar inside. That would have wasted the only pure sample I had. So instead, I decided to use a smaller ampule with a volume of about 40 milliliters. A huge
Yeah,
shout out
downgrade
to the
your
glass blowers
expectations,
at the
but hey, at the
university
very least,
for making this for me
you
on
can get the
such
same
short notice.
concentration in
And
a
of course, a huge
different
thank
vial.
you to Professor Kraus
good enough for a
and
picture.
all his PhD students for letting me perform these experiments in their lab. I connected the ampule to the Schlenk tube, evacuated it, and condensed the blue gas into it using liquid nitrogen. Then I fixed the ampule in a dewar so that the bottom stayed cold, but I could easily reach the neck with a torch. Because of the vacuum in the ampule, the glass neck collapses inward as I heat it. I moved the flame around the neck until it was fully sealed and then slowly pulled off the upper part. By the way, if you enjoy videos like this, I would really appreciate if you subscribed to the channel or even became a channel member.
You should
on
watch this guy
Patreon.
directly.
The link
for one,
is in the video
you can do it
description.
faster than I can.
Every
and two,
cent of your
it's
support
good stuff.
goes directly into videos and projects I am working
I'm just the
on.
reactor. I'm doing
So,
the easy thing.
from the bottom of my heart, thank you to all my channel members and Patreons. After sealing the ampule, it is important to let the hot glass cool down slowly in a sooting flame. That helps release internal stress in the glass and
Yeah, I guess that
reduces
makes
the
sense.
risk of it cracking.
I've never had to
later.
ampule anything before, but
And
it's still.
now, finally, it was time for the moment I had been working toward this whole time.
All right, time to let it
Letting the
expand.
ampule warm up and seeing what color the gas really has. As the gas warms up and starts to evaporate, it initially looks very similar to the sample from my previous video. But not all of it has evaporated yet. Once more of the gas goes into the vapor phase,
Ooh,
the
wow,
color becomes
that is
clearer.
blue.
And honestly, that is a beautiful
That looks like a
blue.
copper sulfate solution.
At this point,
that is
I
super
think
blue.
we can safely say that this is a blue gas and not a cyan one. You can argue about whether it counts as deep blue or not. Personally, if I had been the first person to ever make this compound, I would have called it deep blue, especially for a gas. Compared to my previous sample,
Unlike
you can
liquid
clearly
oxygen,
see the
it's not
difference
going
in
to
color.
explode in your hand
When
with
you
the slightest
freeze it,
agitation.
the solid or liquid is absolutely a deep blue. Because some people asked in the last video, I also recorded a UV vis spectrum of the gas. But there is still one important question left if we really want to be sure that the gas does not suddenly look darker at higher pressure. Does the ampule actually contain at least 1 bar of pressure? If it does not, then everything I have done still leaves open the possibility
you're gonna measure that
at 1
without
bar,
cracking it open.
the color might be different. To test this, I used a simple method. The gas has a boiling point of about -85°C at 1 bar. So, if I put the ampule in an isopropanol dry ice bath at -75°C and see a liquid forming inside, then the pressure in the ampule must be greater than 1 bar. Otherwise, the gas would not condense at that temperature. And when I cooled the ampule to -75°C, you can indeed see a small puddle of liquid forming. So yes, the pressure is at least 1 bar, and this is what the gas really looks like under those conditions.
Nice.
I cannot tell you how relieved I am to finally be able to upload a correct picture of this gas to Wikipedia. The only way to make it look even darker would be to increase the path length. In simple terms, make more of the gas and put it into a big flask. Then you would probably get an even more
But you know, that
intense
would be a
deep
couple
blue
more
color.
months
But
of
that
work.
is
So
not going to be me. I think
Yeah.
I've had enough trifluoronitrosomethane for now. I really hope you enjoyed today's video. Other than that, thank you a lot for watching.
very cool stuff. I very much enjoyed seeing this blue gas because, well, with the mind that I have, I like thinking. I was initially made aware of this gas because I like to browse for random chemicals sometimes, and it also piqued my interest of like if you have a D&D game or some other kind of tabletop game and you're trying to come up with like some you know particular colored gas to use for like a gimmick in some situation. Like, what are some ways you can make your role play more accurate? And I'm like, oh, what are some natural blue gases? And look at that. This is a natural blue gas you could use for something. And then you could say, like, oh, well, my, paralytic gas or whatever is some slight, variant of this or, something dumb like that. But, either way, you could toy with it and, like, just have, something realistic to base it off of. And I don't know, I just think that's neat. and the fact that it's such a simple, relatively simple molecule, all things considered, makes this even more entertaining for me. So, hope you all enjoyed that. We got one more video left for the night. So, let's move on to the funny Australian man. So, this should maybe liven things up a little bit. He's making a gallium lanthanum sulfide glass. I have no idea what's cool about this, but he likes to do a lot of things that involve bright colors as well, because all chemists are secretly children. We all got into the science because we just like different colors. I know I gave a whole justification towards the beginning of stream about the things that I like. It's really mostly that we just like making different colors. So yeah, I don't know why this one is particularly interesting.
Hey, welcome back
but
to another episode
I guess we'll find out.
of Extractions and I. Welcome back to my home shed laboratory. And today's material science project is to make GLS glass, which is a gallium lanthanum sulfide glass. I don't know if this is going to work. As per always with all these Extraction and I videos, I haven't started this yet. I'm not entirely certain I know all the steps.
Brought to you by the color
there,
orange.
But, you know, thanks
just
for
like
coming
last
with me
video.
on this journey. Very quickly, I'm just going to talk about what GLS glass is and why anyone would care, and also what these elements are, because I'm sure lots of you have heard of them, but you probably haven't thought about them very much. And also how we in this
gallium's a very interesting
are going
metal,
to be
or
making some GLS glass a little bit
element.
later on. Well, hopefully successfully making. I can only assume
Gallium
positivity.
is
Let's
the
talk gallium. Now, many people have probably seen, or
Yeah.
maybe
gallium is the only metal in the periodic table that has the ability to be non-toxic, or non-toxic and a liquid metal at relatively close to room temperature. So you could actually play with a liquid metal if you just melt a little bit of gallium in your hand. The only other liquid metal alternative is mercury, and I don't think it's a very good idea to be playing with mercury if you don't know what you're doing. Even if you do know what you're doing, it's still not a good idea. Play with gallium instead.
Even had the privilege of holding gallium. Now, gallium is a fantastic sample because it melts just above room temperature, so you get to sort of hold it and simulate what it was like when our grandparents got to play with mercury metal. In terms of chemistry, I mean, it doesn't come up in chemistry very often. It comes up in physics quite a lot. It's used in transistors and LEDs and that sort of thing. The ugly blue LEDs are gallium nitride.
But the
Gallium
weirdos
is
in
used
material
a lot of
science
semiconductor
chemistry love
materials,
messing
so
with this
it
shit.
doesn't get a huge
And people
amount
who
of
try to
use
do
in
main
terms of
group
tonnage,
chemistry.
but a very wide use.
A
So it's a very
very
essential component of components. That's gallium. Lanthanum is
rather
perhaps more
unexplored
interesting
field.
of these two elements, and by that
Starting
I
to be
mean
explored
it is not
nowadays.
interesting in the slightest. A couple of years ago,
Yeah,
I
no,
did
lanthanum's-
an entire
lanthanum's not
ranking of
interesting.
all the 92 naturally
It's
occurring
the namesake of the
elements, and I ranked them
lanthanum,
from good
or
to bad,
lanthanides,
just based
but
on, you know, vibes.
there's
and
nothing all that
facts and
special about
kind
it.
of thing. And lanthanum came in at 91 out of 92, just ahead of actinium, which I think is pretty unfair to actinium. I think lanthanum probably could have come last. Out of all the naturally occurring elements, I think lanthanum is probably the most boring. Like all elements, lanthanum does have some niche, obscure uses, but you might be asking, does it have any value? And the answer is absolutely not. And the reason that is because it's a rare earth. When you have a rare earth mine, you end up mining all the rare earths because they're all so chemically similar.
God,
and they
that's
all
a
end up
fucking
in the
screen
same
and a half.
deposit. And so you mine all the rare earths, and then you have to spend a lot of energy
rate
separating out
moment.
all the rare earths. So lanthanum, as well as being the most non-useful of all the rare earths, is actually the second most common rare earth. There's always more supply of lanthanum than there is demand. It's basically a waste product from these rare earth mines. I can only assume they're putting heaps of this lanthanum just back in the ground. I mean, when you think about it, right? Think of all the neodymium magnets in the world, right? The things that power hard drives, electric cars, wind turbines, all the little fridge magnets you can buy for like hardly any money. Those, by mass, are 25% the element neodymium. And for all the neodymium that was mined, there was an equal, if not a larger amount of lanthanum that was mined. And that lanthanum is used
In
like
sweet
nowhere.
alcohol.
And we're going to keep needing more rare earths, so we're going to keep mining more lanthanum and just like not using it. So, which does give a bit of context for how we're getting lanthanum for this project, because I actually got it just in my local hardware store. They sell a solution of lanthanum sulfate or lanthanum chloride or something like that to remove phosphate from swimming pools. Once it hits phosphate, it gets solid and then drops out of solution.
best use
so
for the
algae
rare
and
earth
can't use the
element
phosphate to
is
grow. And this is actually, I think this is a
taking
similar
phosphate
procedure
out of
what's
water.
used medically as well, because lanthanum is non-toxic. If a person has too much phosphate or something, I think it's a liver condition or something like that, then it can take phosphate out of their body as well. So each element is not completely useless. And this is an extraction and eye video, so someone will turn up in the comments who has done their entire PhD on lanthanum. I'm looking forward to reading your comment, but yeah, definitely not a super exciting element. But today we get to use
the proper
lanthanum
response to that
gallium
person
to
is,
make
"Look, buddy, you
GLS
spent your
glass.
PhD studying
GLS
fucking
glass is kind of
lanthanum.
an
I think
obscure
you're the
curiosity,
real
but does
loser
have two
here."
distinct advantages over similar glasses. First of all, it is relatively non-toxic. Now, once
Yay,
again, when someone
relatively
says
non-toxic.
relatively non-toxic, they mean that in the usual
A
circumstance,
qualifying
they're
word.
using mercury, cadmium, lead, or arsenic. And in this case, what GLS glass is generally used for is infrared transmission. And generally, when you're talking infrared transmitting glass, was arsenic-based glass, which is where the toxic comes from. Gallium and lanthanum are not that healthy, but they're not that toxic. So compared to arsenic, they are very relatively
You probably
non-toxic. The
shouldn't eat
second
this,
is
but
that
it won't
high
kill you
infrared
instantly. It
transmissions.
won't
And
give you
this is key
cancer.
for a couple of components. It's not as far into the infrared. People often think about infrared transmitting glasses as for thermal vision or, thermal camera stuff. It's not that far. That's sort of the 8 to 10 micron range. This is more in the sort of early infrared. No one calls it the early infrared, but you know what I mean, like 2 to 5 microns. When you think of glass, everyone thinks of, window panes and artistic sculptures, but another thing that, glass is used for in the modern world is the internet, right? Like the internet runs over optical fibers, and those fibers are just made from silica glass. And it's crazy how the internet works. I mean, it's you kind of get the sense that, oh yes,
Internet
I
is
talk
vulnerable
a
to shark
server
attacks.
and I send my signal and then I get it back, and that kind of makes sense. But then you realize that your entire country's data is going over the same optical fiber line at the same time, which turns it into one of the most magical inventions of the 21st century.
It is pretty wild
We've
that
taken normal
internet data
glass
just
and we
is
can put so much
reflecting
information
light
through one
across
tiny fiber.
cables.
It's
It's very
ridiculous.
weird.
Because of, how good the internet is and how profitable it is, research has basically pushed silica glass to its absolute limit in terms of its transmission properties. Like, we cannot get better fibers in silica than we do now. It's crazy that we've managed to perfect glass making to this level. And I when I say we, I mean, professionals. However, there is obviously going to be a fundamental limit with silica, and one of those fundamental limits is that it absorbs actually very strongly above 2.5 microns. So you can never use that silica glass, commercial grade silica glass that we use now for anything over 2.5 microns. And so if you wanted to do that, I don't know why you would want to do that, but we might need to in the future. There might be some quantum internet shit that we've got to do at 3 microns or something like that. And
Already
for that, we would
having
need
to
a whole new range of
plan
fibers.
for the
And
future.
there's a lot of competing
For
sort of
more
different
impractical
glasses,
shit.
fluoride glasses, but also these sulfide glasses. And if you had a 3 micron internet for whatever reason, then you could run it over this GLS glass. So that's kind of why this glass might be important. Whether or not it actually ends up happening with this glass, who knows? But that's what GLS glass is.
Really, the
Right,
graduate
talking
student
about
and
other
professor
people,
want to
how are
research
we
orange
making it? How
glass,
are we making it
and
here?
they have to
Well,
come up
we
with a
have
justification
gallium
for
metal,
it.
and we can dissolve gallium metal into acids and form the gallium salt. And then I feel like, which is never a good thing to say in chemistry, I feel
feelings.
like we can bubble hydrogen
best thing in
sulfide
chemistry.
through the gallium, and it will precipitate out gallium sulfide.
Well, when you feel
Maybe
bad
we
in
might do
chemistry,
that. And
honestly.
we're gonna
When you feel bad in chemistry, that's when you know your reaction's actually going to work. When you feel good about the reaction, that's when you know it's never going to work. Gallium 3 ions with H2S gas to form gallium sulfide. Yeah, I mean that tracks roughly, I guess. Gonna have to give some kind of source of that hydrogen to go elsewhere. Hopefully the minus ion really wants to pick it up.
do the same thing for the lanthanum. We
Probably
already have
not.
a lanthanum salt, so all we got to do is bubble hydrogen sulfide through and hopefully get some of the
Well, I
sulfide
guess
out.
they're
Now,
very
this might not
sulfophilic,
work
so
because
it'll
the
probably
sulfides
it'll
might
find
be
out.
too reactive and it will react with the water that it's in, and it might just get a big mess. But that's where I'm going to start, because we can generate hydrogen sulfide with a method I sort of tried a couple of years ago now.
the
which
candle
is
method.
sulfur and a
Yes!
candle. The bad part about that, which we're going to hit again, is that it really does kind of destroy the flask that it's in. Now, that video I did intend to clean that flask, but
Yeah, you intend to clean a lot of
the
things,
flask is
dude.
still dirty, like several years later. So maybe I'm just incredibly lazy.
This-
but
but
anyway,
this
we
was
can
actually a
generate
pretty
some
cool
hydrogen
video
sulfide,
of
then we
his
can,
a while
make
ago.
metal sulfides out
He
of the
found
metal
an old
salts. Then
paper
we've
from
got
like
the
the
sulfides,
1800s
which we
that basically
just
said
melt
like, yeah, you
together
add a
at high
candle with
temperature, but
carbon
not, like,
and like
ridiculously high. We've had some videos recently.
you can like melt it and burn it and react it to actually form hydrogen sulfide gas instead of using pure complicated reagents to form a highly toxic gas in a awkward setup that might kind of burp back at you. You just basically melt a fucking candle and some like carbon in a flask, and it's like, oh wow, would you look at that? The gas just comes out in droves, and it's very cheap, it's accessible, and you can use much less glassware, so you have many fewer points of like potential leakage. You're still generating a lot of toxic gas, but that's kind of inherent to the territory. But it was genuinely one of his cooler videos out there. Would definitely recommend giving that a watch.
Where we've needed to go in excess of 1200 degrees, whereas I think for this, we probably only need to go to about 1100 degrees. So if we do that, we can melt the glass, pour it out, maybe anneal it if we can get it to a nice glassy state. So that's the steps. Dissolve up the gallium, make hydrogen sulfide, precipitate out the sulfides, melt the glass.
He's also gonna get it. He also gets a hell of a lot of
use
use out of his induction furnaces now that he's like,
but I think it's achievable.
it unlocks all these
Okay,
high temperature
let's get
chemistry
to it.
reactions for him.
We have here
Do all this
two
1100
starting
Fahrenheit
materials.
shit. It's like,
The
yeah, that's no problem.
Barracuda
That's easy.
phosphate remover,
I have an oven that goes up
100 grams
3500
rare earth
Fahrenheit.
salts, but we know from the MSDS that this is pretty much mostly lanthanum. I would say it's technical grade lanthanum, basically a waste stream from the mine that they've turned into a pool product, which is pretty great. And we have this unlabeled Ziploc bag of metal, which is not a great way to store a liquid metal. I got this metal, I mean, well over a decade ago.
Got this
now,
metal from a crack
made
dealer.
a video about it on the first Explosive Fire channel before it got deleted in like, I want to say 2014. And the video was terrible, but not like terrible in a fun way, terrible in like a, it was a bunch of kids with shoddy camera work and showing something not particularly interesting. But it got 300,000 views, I think, which was a lot for the time, seeing as I had 5,000 subscribers. But anyway, that's old YouTube from a little while ago. Anyway, that lump of metal from that video, I guess I just chucked in a Ziploc bag for another day, and that another day has arrived. Reasonably hot today, so we can see it's
Finally,
to melt
only
a
after
little bit.
over a
Don't quite know how
decade
much is in here,
of sitting
so
around and gathering, rust or whatever.
32 grams.
The elements.
2.5 grams. That seems like a lot, especially for this method that we're not entirely certain is going to work, where we dissolve this in acid and then put hydrogen sulfide through that acidic gallium solution. Actually, it's not going to work at all if it's acidic. So it's got to be neutral, but then maybe we'll precipitate out the gallium oxide. Anyway, I have a lot of problems with this method. I'm not convinced it's going to work very well. So maybe
she'll be
we'll just
right.
get out maybe 10
sure you
grams
figure
or
it
so of this, and we don't need to break up this metal. We can easily melt this metal. I'm just going to immerse this Ziploc bag in some hot water, and we should be able to syringe some out, which is a very cool property of dealing with this metal. Just melt the metal and move it around as you wish. Very cool.
Now don't forget to get that random tail of gallium that you've kind of got growing, that you let it
Metal.
condense out on the left side of that bag. Maybe he doesn't need that much, I guess.
Okay. Maybe it doesn't react. I'll find another acid, I guess.
I mean, you could warm it up a little bit, increase the surface area, make it more reactive.
Bubbles. Let's add a little more. A couple more mils.
Also, noting he's basically making aqua regia without intending to. Did just combine hydrochloric and nitric acids together. That's definitely overkill. He's making very, very dilute aqua regia, but still. It's funny he unintentionally did such a thing. It's overkill for something like gallium. Oh, that's cool to see it beat up like that. You don't get to see liquid metal do that very often unless you work with mercury and poison yourself.
Just gonna move this outside. Quarantine.
Ah, there you go. Now you're getting that classic nitrogen oxide brown color that we were seeing in the previous video. Or yellow, I guess.
Alright, so the gallium has been reacting in this acid for the past, couple of days, really. It kind of stops reacting pretty much altogether when I stop heating it, and it was a nice clear solution for most of it, but then right at the end here, I don't know, it's turned into milk. It should be dissolving. The solution's acidic. It's not like crashing out with crystals, but I don't know. It just seems like a little bit of maybe hydroxide, I guess.
Yeah,
refusing
carbon
to
dioxide from
redissolve
the air
back into
forms
the
some
solution.
hydroxides.
So my patience has run
Insoluble.
out actually for it. It doesn't look like it's a heat that's out of solution. So I'm just going to filter it, and then we can
you gotta
get
do your
to the
reactions quick,
hydrogen
Tom.
sulfide part. It'll be a nice clear solution, ideally, after filtering. While that's happening, let's go create our hydrogen sulfide generation system. All right, let's do that. We have here our 3 reagents for our hydrogen sulfide reaction: sulfur, some amorphous non-conductive carbon, and a candle. We're just using this as our paraffin source. People, very rightfully so, commented on the last video I used a candle that it's just very cheap to get big blocks of pure paraffin rather than using a candle. But first of all, I forgot to get nice paraffin for this, but also it's just funnier using a candle.
It is. There's more aura to using a candle rather than pure paraffin. You entirely use this reaction method because you don't want to get actual reagents. You want to use a fucking candle and some carbon from like a aquarium filtration, supply store. It's more fun. And sulfur from like a gardening, gardening aisle at Lowe's.
Put some actual glassware on there.
More interesting this way.
More like science.
Actual glassware uses a fucking plastic cup. Exactly. It reminds me of something else I want to do that does also technically generate hydrogen sulfide at some point. Is like, I would love to make a alternative thermite. So thermite's normally iron oxide and aluminum powders, but you can also get a thermite going using sulfur and I believe aluminum powder, just regular aluminum powder. That would form aluminum sulfide when you light it up quickly, hotly enough, and it would form a molten 3000 Celsius thermite. It does also, unlike regular thermite, put off H2S gas, though, so toxic.
At least it looks good.
It doesn't burn, that
most of our gallium solution down through there. It's nice and clear, so we will move on to the next step, which is setting up the whole damn hydrogen sulfide generation and seeing if it works to produce gallium sulfide, because we may have done all this and it's not going to work anyway, but we'll have some optimism. We'll go set up some goddamn poison gas generator. Let's go.
Yo, poison. I love poison. H2S gas is not something to mess around with, though, if you're not ready for it. It is literally as toxic as carbon monoxide. You can at least smell it a hell of a lot better than carbon monoxide, but it is not to be trifled with. I guess the chemistry going on here is something like
failure. There's
a
bit of
failure
solid in the flask, but I think that's just because I was adjusting the pH with some sodium carbonate and I was trying to get it a bit more neutral. When you start putting it neutral, then the gallium starts precipitating out as gallium hydroxide, but if it's acidic, then gallium sulfide is going to react with the acid. So I just don't think this is going to work, and we generate a lot of hydrogen sulfide. You can see that's our bleach solution. The bleach oxidizes the hydrogen sulfide into sulfur, so that's why it's all yellow and chunky there. It's all yellow all through here, thanks to all the sulfur precipitating out, and got a little yellow tinge in there, which I think was a little promising because what we were trying to make is yellow, the sulfide, but I'm pretty sure it's just sulfur getting blown off out of here into there, which sucks. So that's a trash yellow. It's all trash yellow. I gotta clean all this. I was gonna try also with the lanthanum chloride here, but yeah, look, hey, if this doesn't work, then I'm not going to try again with this and not have it work. This is a mess. It stinks. It's been cooled down for a couple of hours now, actually, but there's still a lingering smell of, it's kind of burnt tires and piss rather than just being like stinky farts from the hydrogen sulfide.
I mean, those are
Sulfide
still
is like
sulfurous
rotten egg
things, so.
Fart smell, really. But when it's kind of pure like this and there's just so much sulfur, I think it's kind of a bit more acrid, a bit more kind of burnt rubber smell. It's not particularly pleasant. Yeah, it's actually extremely unpleasant. Let's put it that way. Damn. Anyway, so I'm gonna clean this up. This flask. Yeah. Fuck knows. But more importantly, what are we doing now? This is step 1. We don't have any gallium sulfide. How are we making gallium sulfide? I've got to think about that.
Try the same thing again.
The synthesis of gallium sulfide. It comes from France in 2020, and it is a mechanosynthesis. So they took gallium metal, we got another lump here, and sulfur, grinded it together, and formed gallium sulfide. Simple enough.
Yeah, I mean, I guess that makes sense. Sulfur
I say kind of
oxidize
because they did use a plenary ball mill, which is like a high speed.
It's not usually
really
strong
good
enough for that directly.
Ball mill. And it was also done under an inert atmosphere because the stuff is reactive to moisture in the air.
Oh boy.
So not entirely certain we can do it with what we have here. We've got
he's going to half-ass it.
Which we used somewhat recently, but is somehow already covered in cobwebs.
Yeah, so you somewhat recently covered in a spider web already.
What's the material out of this? Ceramic.
God damn Australia.
But that's
giant spiders everywhere.
Which we last used for the perovskites.
And it's still fucking radioactive green. Excellent.
Crazy. Anyway, so that's still covered in lead perovskite, which somehow is still completely stable. Okay, that's very funny. But if we clean this off, then we should just be able to add some gallium and some sulfur in here and grind it. Hopefully, it stays dry enough to make some gallium sulfide.
See, it's funny. I used to think like, oh well, you know, he is working on his PhD.
It went reasonably basic and precise.
Like that's why he just never has the time to clean up anything. I get it. It's totally understandable. Now he's well past graduated. I guess he does still work a job, you know, like a postdocing job after this to, you know, earn money. But like, I feel like he should have maybe a little bit more time nowadays to like clean up his shit, to clean up after himself, so he doesn't end up having, you know, to clean up as he does his work. But I guess it's part of his style and his brand at this point. So why change it now?
Stuff, but it's a bit sludgy now. It's verging on being a paste, but I'd still call it a sludge. I reckon we can recover the gallium metal from this. We'll come back to that. We'll put that to the side.
Right, you'll come back to it.
To do chemistry a little bit here, but we'll try
in
this
like
kind of
5 years when you need more
mechanosynthesis.
gallium
I don't know why
or
I think
something.
it's bizarre.
For
It's
some
just always
reason.
weird to think of doing chemistry by just taking two elements and grinding them together to make the thing. I guess maybe it's also bizarre because this is like going to be a liquid metal, but I guess when we're grinding it, we want it to be a solid. I don't know. I don't know why I'm overthinking this. Maybe I'm overthinking it. Maybe I'm underthinking it. Maybe I'm
It just feels bizarre because chemistry usually happens in like solvents and
goddamn, we
liquids.
cannot grind in it now with that much lead contamination.
And
So
you always have like
let's,
some
gently wash
tertiary
this with a
dancing
little bit of
partner
acid,
kind of
and
thing,
that
or
should
it's
destroy the
gases interacting
perovskites,
correctly.
solubilize
Not usually
the
just
lead,
two
and then
elements.
we can ditch it away.
It's a little barbaric.
And store all the lead waste somewhere. Beautiful stuff. All right, that's step one.
Especially when the barbarity is usually like, well, the barbarity is especially apparent with something like this, when it's just like we're literally using, you know, these alumina balls to smash the elements together. It is literally the most kind of grug do chemistry kind of
It's broken.
idea you could think of. Oh, good, he broke his
side. You're always the worst of the lot.
Unfortunate.
God damn it.
Delicious, delicious lead. We can't have any of that in our non-toxic glass. That's the whole point.
Exactly 10. Okay, so we have our clean and dry, lead-free media here now, which is good. It's been
Lead-free,
desiccator,
also an
so
asterisk.
It dries it off because we don't want any water reacting with gallium sulfide as it's being formed. We have, oh, sorry, ignore the vape here. That's it's a different project. We have 12 grams.
And we'll see that in
gallium
3 years.
sitting there's a nice little puddle of liquid there, and 9 grams of sulfur. The exact stoichiometric amount of sulfur to react with, you know, all the atoms of gallium here is about 8.2, 8.3 grams. So 9 grams is about a 10% excess. They do this in the paper. Mostly they do, you know, just the stoichiometric amounts. But here I want to use an excess of sulfur just to try and stop the gallium reacting so much with the air when it's, you know, ground up into little particles and making so much gallium oxide, and also just making sure that there's definitely enough sulfur, because if we don't have enough sulfur and we've got too much gallium, then
You know, it also helps you're
sulfide
using
we
like
make is
gardening
gonna be
grade
all
sulfur.
weird,
I'm
but
sure it's not the
excess sulfur
purest.
shouldn't really affect it at all. In fact, we're just going to be heating
Hey,
this up
Proto.
later when we're making the actual glass, and the sulfur will just boil off at that point. So I don't mind having excess sulfur. In the paper,
He's our favorite Australian man is up to making gallium sulfide, lanthanum sulfide glasses, which are orange, and that's their most interesting property. But the people who are writing the papers about these glasses are insisting upon them being useful for the next age of the internet, when we need to, for quantum computing, transmit light signals under 3 microns long, and that's something that our current silica fiber internet cannot do because of physical limits on silica absorbing light in that range. Whereas we need something that can reflect the light and pass the light through, and that is something that this orange gallium sulfide, lanthanum sulfide compound glass can do. So he's making some because it's fun. Thought quantum computing was a myth, a fairy tale? No, it's very much real. It hasn't become, anything commercial. It's probably going to end up being, certainly at first it's going to end up being basically a research tool to try to solve quantum equations using quantum hardware, I guess. I guess it's hardware. But no, it's very real to have qubits being calculated like that. It is a new yet established field at this point. Quantum computers do tend to exist at major research universities, and they are doing things with them. I'm not really sure what they're doing with them, but I'm sure that if you got one of those quantum computing scientists around, they could tell you all about it.
When they use a 9% excess, they get different crystal structures of the material that forms, or like the ratio of the crystal structure. There's a beta form and a gamma form, it's just the spacing.
But we don't care about that, because we're going to smash the different forms together anyways with the lanthanum sulfate
this doesn't
layer.
matter because we're heating it, and when they heat it above 450 degrees, it all resets into this alpha phase anyway. So we don't really mind about this polymorph stuff. So that's what we have here.
I hope Pro, you and everyone else had a good...
really want to protect this from moisture. It's so absurd saying this. Previously, I was trying a synthesis.
A good meeting with everybody else.
It's not going to work. Anyway, I'm not going to get hung up on that. So we're going to run it in this bad boy, the tumbler. But we also kind of
gaming PCs have quantum parts. Aren't you forgetting about the hungry AI companies and their quantum parts?
And I assume they have probably a nicer setup than this.
They'll use all of them
I was
first.
wondering if I could run this,
run the quantum parts up several $1,000s.
This chamber, I'm not going to be able to seal it, but it's probably fine for me to just mostly seal it and then just flow argon in, and then the argon will keep flowing out, and it'll keep a lot of the air out. I don't know. It might help at least protect the gallium sulfide a little bit. It's probably going to look ridiculous though. So
just gonna dump that on there. Oh yeah, and he's doing all this air free because the paper did it air free to bash gallium and sulfur in their elemental forms together to get gallium sulfate.
Is that too ridiculous?
Or gallium sulfide. Brilliant.
I've built worse. I know that's not saying a lot, but so ridiculous. This video has been such.
This is the most half-assed air-free system I've ever seen.
That's so funny.
It's not even going to be air-free.
Doing this. All right,
he's got a fucking wire going out under it.
Brush that down a little. Very large.
Oh, the things you do in a garage. The ring that transforms magically from blue to red.
Alright, it's gallium time, let's do it.
I guess, yeah, you do want to transfer it as a liquid, but, like, it's gonna not pour out very well. If you're gonna grind it anyways, you might as well just throw in a big solid block. Whatever. He's the science man, not me.
Alright. Go.
A lot of hungry chemistry analogies tonight.
It's only been a couple of minutes. Only been like 4 minutes of grinding.
Oh wow, look at that.
There's some green. It's looking kind of green.
Previous video, guy was talking about, I want to eat this disgusting nitrosyl chloride red liquid. I'm not so sure about that.
In what's going on. I got the argon flowing. Hopefully the powder doesn't fly everywhere.
Alright, time for the powder to fly everywhere. Well, he's losing a little bit of product here, but for the sake of the video, I'm glad he did it this way. Now they all look like they're covered in volcanic ash. Sped up speed, very. That is pretty cool, though. Like, it reminds me, like, I have a small vial worth of elemental silver that I made once out of reacting copper with silver nitrate.
Turn the argon off as well. Oh man, that's
It's fun to just have pure silver
I
on
used
hand.
about a third of the other cylinder, the last third, and maybe 2/3 of this. So probably about $100 worth of argon I've used for this.
$100 of argon.
I haven't looked
You could
at
have
this
just
for a little while.
bought
It's had
the
probably
gallium
3
sulfide
hours
probably
of
for that
grinding,
price.
Maybe a bit longer, but an hour or so was last week, and I stored it in a desiccator, and I've done a couple hours today, but I haven't really looked at it the last 2 hours or so. It's been, I mean, roughly sealed because it's absolutely pouring with rain, and we're making a moisture-sensitive compound. And I mean, last time we looked at it was black, which I think is really gallium sulfide. The French paper that we're following was very kind enough to actually give images of what
Wow,
they're
that's
expecting
uncommon.
the material to look like. And so
Usually they just call it an off-white solid.
Metallic gallium
Call it
and
a day.
yellow sulfur, but theirs goes to this black gallium sulfide very quickly because they're obviously using a much more optimized grinding system than whatever the hell this is. At least I think so.
Yeah, I can
I'm
coat some
losing
bullets
touch
in
with
pure
the
silver.
ball mill
Pure silver
community,
dust.
You know? What am I saying? So it's this
It also
black
makes
gallium
for
sulfide, and
good
then it
gifts
goes,
for people as
unfortunately,
well.
it goes
I've
more
done that
yellow,
before, and they're like,
that's
"Oh
what
wow,
actually
that's kind of
looking
neat."
for. So we are actually
I didn't really want this,
it's
but it's kind of
gone
neat.
a little yellow rather than pitch black because we want this gallium 3 sulfide, so Ga2S3. That's what we need for the glass rather than just gallium 2 sulfide, which is gas. So I did heat it up at some point. If it was above 35 degrees or so, then any little bits of gallium would melt, and I think they're going to react a lot faster as they get ground down. Because when we looked at it about an hour in, you could tell it was black, but it had little flecks of solid gallium metal in there still. So I did have to heat it to get it going, but it's still quite warm, so I expected any gallium would still be liquid. Not that there should be any gallium left anymore, it should all be gallium sulfide, hopefully. But it's warm just from the grinding, but also from this motor. Alright, I'm nervous, you know. If it's still black and still looks like it did after an hour, maybe I just gotta add a little bit more sulfur and then just keep grinding it, but I don't want to keep grinding forever, you know. I gotta retire at some point. Have I built the suspense for the reveal up enough? Because
Tiring to grind
sometimes we get
forever.
incredibly
I don't have that
disappointed
kind of
with
leg
this.
strength.
Oh, so the bit where I said there shouldn't be any
Ruh-roh.
gallium, there's definitely
Still a lot of gallium.
liquid metal in there, right? Did I measure my ratios wrong? Ooh, this feels...
I do imagine it's probably just
Maybe
because the
that's why.
sulfur is
Getting it
kind of
out
crappy
and stirring
quality.
it. Okay, well, I guess I'll have
probably
to
not
do what
all
I
that
said,
pure.
which I don't really want to do, but I suppose I have to do what I say sometimes, which is just add a little bit more sulfur and get this grinding again, because I guess there's just too much gallium. Got to stir this all up too. It's not really a very optimized grinding setup, which is saying a lot. But the fact that we're making a moisture-sensitive compound and it's very close to working, it seems, while
And it's not
raining in my
completely
shed
terrible.
here, is good.
It's actually
is
kind of
good.
impressive.
Okay, let's go find the sulfur. I'm going to add a full gram more. We'll add an excess, burn off any excess anyway when we're heating it. Just want to see if it changes from this black.
Adding steel balls for some reason. Okay, interesting. Getting angry at your chemistry is always the best way to make it start to work.
I'm done with this. I'm so done with this. This has had many hours of grinding. Whoop. Many hours of grinding across multiple days, across multiple weeks. I'm sick of this. What we were waiting for is this black powder, which is, I guess, a mixture of gallium 2 sulfide and gallium 3 sulfide, so the GAS and the Ga2S3. And we wanted to see that lighten in color to kind of indicate that we're going to a more pure Ga2S3, which is the compound we want, the stuff we need for the glass. And it really hasn't lightened in color at all. In fact, what it's really doing is sort of just like coating all the media in a way that I can't seem to clean off very well or kind of knock off to allow it to keep grinding. My solution was just to add more sulfur because
Ah, that gallium powder, delicious.
it's getting to the point where we shouldn't do this inside, which is a great sign but there is a hydrogen sulfide smell. Yes, increasing the sulfur in this reaction mix should hopefully drive it towards this Ga2S3 because there's kind of like more sulfur per gallium. And so I added an extra gram of sulfur and then like another gram of sulfur, and then ended up adding in total another 12 grams of sulfur, which is a huge amount. This mixture has heaps of excess sulfur, which
over
doesn't look
double
great,
the
because
amount
once
of
again,
sulfur.
It's still incredibly black. This is mostly bright yellow sulfur, and it looks like this. So I'm going to heat this. I'm going to heat this to 350 degrees to try and drive off that excess sulfur, basically boil it off, and then hopefully maybe the stuff we're left with is at least reasonably pure gallium-3 sulfide. And do I have any reason to believe that that would be the case? No, not really.
But blind hope
This is
sometimes,
all the time I can
you know,
spend on the grind without going insane.
works.
The grind life is not for me.
It might make, you know, all the
I'm
heat
gonna
might make
get
it
out some
react
black
more.
powder, put it in
Sometimes
here,
that's
and
the
then
principle
heat
you
it
need to
350
work
degrees. Hopefully it doesn't reek too much. I mean, a great sign is that this does smell very bad, and it does react very lightly with water to form hydrogen sulfide, which is this horrible smell. It's a very toxic gas, very detectable in small amounts. So great that it can produce this toxic gas. It means it's the compound we kind of want. But the fact that it doesn't kind of completely react means that there's only some of the compound we want, and a lot of it is the compound we don't want, and I guess excess sulfur. So like, we've made the thing that we want, but it's just not at a good purity level. I mean,
Yes, you made it kind of poorly, like garage quality.
It's just not going to be good enough for glass forming. So that's a reality, but I just can't keep this grinding forever. Like, I'm going to go insane. This project has actually been going on for months.
Not your longest going project. Remember that one time you grew plants for 3 years? You get a moderately energetic organic?
So a little bit of
I bet that one was fun, Tom,
nothing
huh?
has gone our way this video, but let's give it a shot. Let's give it a shot.
Well, I saw the sulfur vapors there. Didn't see them elsewhere, but... Well, now the entire thing is coated in sulfur. Good work.
That's one way to boil off the sulfur, I suppose. Whoops. Here we are. We end up with a vaguely strange, metallic, alien-looking material. I mean, it's certainly not gallium metal. It's certainly not sulfur. It's definitely not gallium oxide. So, you know, it's definitely
Kind of looks like the byproduct of like the Pharaoh snake reaction. It's not
gallium sulfide for our glass is yet to be seen.
A good sign.
This is as good as I'm gonna get it. I think I'm definitely gonna carry that forward. Wow, that was a bit intense. I mean, I'm pretty bad at predicting the timelines for things to happen in this project. I mean, that's exactly what I wanted. The sulfur to kind of boil off, but I thought it might take maybe half an hour, but it really happened in about 2 minutes. In fact, it basically all boiled off in about 10 seconds there at 350 degrees, which in hindsight is actually not that surprising. And did burst into flames there, which wasn't great. And we've sort of yellowed my furnace, but hopefully that'll cooks off. I'm glad it wasn't any larger scale, otherwise that would have gotten a little bit more hairy. Look, hey, it's what we wanted. The grinding took an extra 4 weeks, but the sulfur boiling off happens pretty much instantly. So, you know, that's a time save, I guess. Look, hey, we've made the gallium sulfide, the G of the GLS, and I guess half of the S. But we got to turn.
You probably could have still made the original gallium plus
lanthanum sulfide. So we've talked about
gallium plus hydrogen sulfide gas method work. It works for a lot of other elements. Probably just had like a, I don't know, a bad candle or run.
How difficult it's been getting the gallium
Waited too long to use it.
Lanthanum sulfide, I think, is more reactive, so it's going to be harder to make. So I'm going to go see if I can buy some.
Now you're going to go decide to buy something.
Package straight from Poland. Lanthanum sulfide. So this is the one we want. They also sold this one. I just thought I'd get them both, just in the off chance I was wrong about which one we needed. This is only 3 grams, but it should be enough to make at least a bit of glass.
Surprised you didn't buy some gallium sulfide as a backup, you know, and good quality. Oh, he did.
Big lump of lanthanum metal in there.
Or
I
not.
don't know really what I'm going to do with it, but thought it's a lanthanum video, you know, I might as well buy it. Actually, whenever I film the intro, I said something like, oh, lanthanum has no value, you can barely even give it away. And it's funny because then I paid for 100 grams of this, and then the guy at Onyx messaged me and he was like, oh, I've given you like 130, 140 grams. It literally just gives away more. He's like, well, I don't want this shit. It was pretty cheap, and he was still like, nah, I'll throw in some extra. Like, no one wants this. And I think that's, well, actually, no, it's not quite it. There should be one more. Yeah. I don't know. It's just a bar of palladium. The palladium price has like plummeted recently, so it's now back to normal levels. I don't
does have a little bit of obsession where he just ends up buying
complete
extra stuff he doesn't need.
Easy, isn't it? Chemistry's easy.
He's just like kind of window shopping for something, and he's like, ooh, I want big lanthanum chunk. That sounds fun.
Here we are.
It's like, that's not in your budget for this video.
So we have here lanthanum sulfide that we
sure,
bought,
bud.
just a bit less than 1.5 grams, or about 1.5 grams. I've already forgotten the number. And then our gallium sulfide here. And I know what you're thinking. This looks exactly like what we wanted it to. So did I cheat? Did I buy some new stuff? No. I've been keeping that weird metallic stuff that we made the other day, or like metallic-y looking stuff. And when I ground it up into this powder, it looks exactly like what we want.
How about
the
that?
Optimism is absolutely flowing through me today. I couldn't believe that when it like ground up to this nice yellowy green powder. It's still
I guess sometimes just a physical kind of manipulation like that can make shit work. So good job, you got lucky.
Sulfide, 30% lanthanum sulfide by molar weight. So, you know, 70% of the atoms are gallium, 30% are lanthanum, and that seems to be the standard for this glass, this 70-30. There is a glass forming range which varies with the different in composition. So outside of that range, it doesn't form a glass, which is kind of, I guess, a little bit weird to think about, but the glass is really more of like a frozen liquid, and the atoms kind of get confused and don't crystallize. So you've got gallium sulfide and you've got lanthanum sulfide, but you don't have crystals of lanthanum sulfide mixed with crystals of gallium sulfide. You just have a mess of all the atoms.
You kind of want to just push the mixture like over the edge
and frozen.
to get
that's what we want. We want to
moving,
this nice glass,
but not enough
to melt it together, and then it'll melt, and then we'll cool it
get
down
too kind of flowy and everywhere with each other. Then you have to like cool it quick.
Here at 400.
Very
sure,
quick.
Why not? 400. The papers we're following does a 350 degree preheat.
To lock it in that liquid-like structure.
Sure. That's my problem. I have to change something. Always have to change something. So we're just going to load it into here. This is a pretty standard alumina crucible. Hopefully it all fits. And we're going to leave the lid off for here because we want to just drive off any last volatile stuff, like any leftover sulfur. We're still looking a little yellow from the other day. And then we need to heat it up.
Crucible's looking a little yellow too, my man. Is that Phil perovskite still?
Goes up that high. I think 1,150. All the damage from it was me setting it to its maximum temperature, and then all the paint starts peeling off. So it's not particularly nice for this furnace to go up to its maximum temperature, and the stuff we're making is still reasonably reactive, so the longer we have it heating, kind of the worse it is. So instead, we're going to use the equally dirty, or in fact, potentially even more dirty, fan favorite microwave, and the microwave furnace. So this is a little thing off eBay, which I've used a couple times now. It's just
that microwave looks like it's been sitting in the fucking rain for the last 4 years.
Absorbs some microwaves, so it gets super hot in here very, very quickly. So put our crucible after it's preheated.
I know it's just a crappy lab synthesis microwave, but still.
Should get to 1,100 degrees reasonably quickly, like within 10 minutes or so, 10 minutes of microwave cooking. And then hopefully it doesn't all spontaneously decompose into sulfur and hydrogen sulfide and burst into flames. But equally so, I hope it doesn't just stay as raw powders. I hope it does melt and we can see a glass. Just want to see the glass form. All right. I've needed positive vibes for the entire project for this, but this is where I need the most positive vibes because there's a chance this genuinely works. Despite everything going completely wrong for this entire project, over the next hour, we could see results, and that's crazy to me.
You want good vibes, Tom? You gotta start playing happy music.
Time I use this. I hope it still
Everyone knows that the chemistry can listen to what music you're listening
let's
to.
Mix and just hand grind.
It tends to like Marvin Gaye.
Before loading in the crucible. And let's get it damn cooking. All right, positive vibes. Thank you.
That's oh my fucking god. Really? Oh, that's a shame. They say he has the least stable hands in the West. Except he's actually in the East.
Good. Pretty hot. The album's pretty hot. Oh yeah, great. Everything's fine.
The microwave on fire back there? Does it smell weird? Spill it again. Do it. I wish he would just purchase like a pair of tongs that like actually has a loop at the end of it. You know, just so it can form a nice circle around the circular things he keeps grabbing with it. I know that costs him an extra like $60. It's out of his budget. He could buy 170 grams of lanthanum, but you know, a pair of tongs with a loop on the end would just be too much to ask. Ooh. I mean, hey, I wouldn't doubt you could possibly get glass from this instead of having to go and use the big furnace. I mean, shit. A lot of people just tend to overlook microwave synthesis. It's kind of not... Oh, well, now the glass is broken, but it's kind of... microwave synthesis tends to be overlooked as just kind of like not... what's the word? It's just not very typical, and it kind of has this almost, you know, home chemistry sketchiness vibe to it that just tends to be, you know, something you avoid in the lab. But it is genuinely a really useful technique the occasional few times you can use it. So why not use it more? And look at that. Now you can just do a simple remelt. Of course. You probably could have just melted it in the previous crucible instead of sacrificing it, but, you know, he wanted to see if he could just smash the crucible and get the glass, but see, get some fucking tongs. Get some fucking tongs, dude. Ones that are actually circular. Not hot enough. Right at the edge there. That's what happens when you use also a shitty kind of, you know, picnic table. Start burning it. Ooh, look at that. Saw that little piece of glass hit that metal plate down there. Got a nice glass bead for his troubles. But still can't get everything else to pour. And I'm guessing it's probably like 2 a.m.
It's the dead of night now. I'm nearly at a loss for words, which is saying a lot for me. This looks exactly like it does in the papers. It's orange glass, transparent. It's exactly what we want. I thought at most we would maybe get something that sort of resembles a glass, but the fact that it's worked this well, we managed to actually pour some out. Of course, very limited by my sort of glass handling skills and pouring, but I didn't feel like I could hold a blowtorch to this glass because
those are pretty nice glass pieces. I mean, they're very small, of course, but
weird to
cool.
think about. Tick for the microwave furnace again. That's incredible. Thank you for your positive energy. I hope it comes across how unlikely that was to come together. That's amazing. All right, well, thank you very much. I'll see you next time.
All right, that was a. Oh no, Niall, not you yet. No, you're there for another month. But no, that was neat. I don't know. I don't really have much to say. Honestly, I've been kind of out of a lot of things to say today. But oh, let's get a good picture for me to yap over. Yeah, look at those. Cool little pieces of glass. I love glass chemistry. It's such a I won't say super niche, but it's something that a lot of people tend to shy away from in their actual research because of the fact that glass is not orderly and structured. So it's just not, you know, easy to deduce things from and hard to predict how it's going to work. And there's a little bit more of an art to it rather than hard science. So people tend to shy away. But, you know, glass chemistry is really cool. It's... you end up getting a lot of transparent stuff with a lot of cool colors, and that transparency is not just aesthetically pleasing, it's also, functional. Like Tom was saying at the beginning, people think about this for, quantum computing, fiber optics, stuff like that. So, and then you also have different glasses for like the fact it's transparent means it absorbs light all throughout it, so it could be used as a volume to facilitate reactions with. It's all really neat stuff. But I think that's about gonna do it for me tonight. I can tell that I'm running on fumes just a little bit. So, um, thanks everybody for tuning in, even for a little bit during tonight's chemistry stream. I will be back next week to finish off Freedom Planet 2, and I'm guessing finish off Freedom. I have to at this point. I did all the Battle Dome stuff. Finish off Freedom Planet 2, and then probably do a small Mega Man project. I still have to decide what I'm going to do on Monday, and what will likely bleed into the week after being my final stream for until August. But you'll see the schedule eventually, so we'll get there when we get there, I guess is what I'm saying. I have a Discord down below if you want to hear us talk about a little bit of science. I'm always down to talk about science and chemistry and stuff like that. We mostly talk about Mega Man and a couple other things though, but more science people are always welcome. I could use a couple fellow scientists to talk to. In addition, I have my Twitter and Blue Sky. If you feel like following those socials for some reason, you're very much welcome to do so. And then be sure to share this with your local scientist and your local glass blower, because I'm sure they would enjoy this video. Do all the interactive stuff with the video because it helps me grow and it helps me feel good about myself. And it should make you feel good about yourself too. You'll get a sense of accomplishment in boosting a small creator, isn't that right? Anyways, rambly time. I'm gonna go to sleep soon, so have a good night, everybody, and I'll talk to y'all next week. Bye.